Hello. We're going to start talking about Chapter 20, Lecture 20. So in Chapter 20 we start talking about redox reactions, we talk about electrochemistry. So the very first part of Chapter 20, before we really even get into Chapter 20, we're going to review redox reactions. Okay, so redox is reduction plus oxidation. Where we have transfer of electrons from one species to another. Reduction is gaining electrons. Oxidation is losing electrons. So when a substance is oxidized, it gives its electrons to another species. Hopefully this is review for you. We will go over balancing redox reactions in much more detail, but we're also going to be looking at oxidation states. So oxidation states is a way of assigning a charge, assuming completely ionic bonds. So your electrons are going to transfer from the species that is less electronegative to the species that is more electronegative. So the oxidation states for an actual ionic compound will be their actual charges. But for a non-ionic compound, we're going to have to solve for oxidation states. And I'll go through how to solve oxidation states. There's a lot of steps in it in the redox video. But we will look at how to solve for oxidation states. If you get a chance before we go into lecture, brush up on those so you can determine oxidation states on your own. You should know what an oxidizing and reducing agent is. Remember, an oxidizing agent is going to be something that causes something to reduce. Or, sorry, something that's being reduced, so it causes something to be oxidized. And it causes something to be oxidized by being reduced. And then our reducing agent causes something to be reduced by being oxidized. So the thing that is oxidized is the reducing agent. The thing that is reduced is the oxidizing agent. So to be able to identify redox reactions, you have to be able to identify when oxidation states are changing. So make sure you're able to do that. But we will go over that. And then we'll get into the lecture itself, where we start out talking about balancing redox reactions. And we're going to look at balancing redox reactions in acid and base. Okay, so we're going to use the half reaction method, where we divide our reaction into the oxidation half and the reduction half. And pretty easy. Our steps for balancing is after you break it into your half, you're going to, steps. Break into half reactions. Okay, so you'll have your oxidation half and your reduction half. You have to know what's going on with your oxidation states to know what's being oxidized, what's being reduced. So make sure you know your oxidation states. After you break it into half reactions, you will balance the elements. You're going to do non-oxygen and non-hydrogens first. Then you're going to balance oxygen by adding water. And you'll balance hydrogen by adding protons. Okay, this steps acid and base, right? Sorry. So after we've balanced out our elements, we need to balance out our electrons. So you're going to add electrons to the more positive side of the reaction. So if one side of your reaction, all of your charges add up to +1, the other side of the reaction, all your charges add up to 0, you'll add 1 electron to the other one, so you get both sides to be 0. Okay? As a note, you'll be adding electrons to the product side of the oxidation, and the reactant side of the reduction. So if you know which one's which, you can do that. Then you're going to balance the equations against each other. So we want both of them to have the same number of electrons. Because whatever electrons are being or lost by the oxidant are being consumed by the reductant, so you have to have both. And you'll just multiply to get multiply by the smallest whole number multiple to get the same number of electrons. For instance, if one produces 2 electrons, one consumes 3 electrons, our closest divisible number would be 6, so we need to multiply by 3 for the 2, 2 for the 3 to get 6 electrons for both. Okay, then at this point you're going to add your half reactions together. Okay, and for your acid, done. If you are in base, we have additional steps. You are in base, there is going to be no protons, so you need to get rid of the protons by neutralizing them. So we're going to neutralize H plus by adding an equivalent amount of OH minus. Remember, H plus OH minus gives you H2O. But you have to add it to both sides. If you do not add it to both sides, you will not have a balanced equation. So you must add hydroxide to both sides. So one side of the equation, you're going to take your protons and you're going to add it with your water, and you're going to produce your hydroxide, and you're going to produce water. On the other side, you're going to have excess hydroxide, and that's fine because you're in base. After that, check for water on both sides. Let's cancel out. Excess, and then you're done. Okay. So, balancing those are going to be the biggest part of this, but we're also going to start talking about electrochemical cells in lecture 20. So, electrochemical cell is a device capable of generating electrical energy from chemical equations or facilitating chemical reactions through the introduction of electrochemical energy. So it can use reactions to produce electrical energy, or use electrical energy to facilitate a chemical reaction. The first one, right here, is a galvanic cell. And then the second one is an electrolytic cell. So galvanic cells, that's how a battery works. And electrolytic is like charging a battery. Okay. So with our galvanic, it's a spontaneous reaction occurring. With a electrolytic, this is a non-spontaneous reaction. So we have a non-spontaneous reaction that is being facilitated by the addition of electrical energy. Okay, we're going to talk about the components of a galvanic cell and how they work, and look at components of a galvanic cell. Basically, a galvanic cell, we have two half reactions in beakers. We have an electrode in each. Generally, the electrodes are made out of metals, but not always. These electrodes are connected by a metal wire. Usually there's a voltmeter just to see what type of voltage is being produced. And then there's a solution in here. And then there's a salt bridge. So, not the salt bridge, the salt bridge. Electrode works by our half reactions occurring, and when those half reactions occur, electrons move from one species to the other. So you're going to have electrons moving, and then you're going to have anions moving as well across the salt bridge to equalize charge. If your electrons are moving, they're going to move from our anode to our cathode, like so. So what happens is the anode produces the electrons, the cathode takes the electrons. So if we are producing electrons, this has to be an oxidation reaction. And then the cathode takes electrons, and here is where reduction occurs. And it's separated in order to actually harness the energy that's produced during this flow. But of course we have to have our anions go towards our anode as we are removing electrons. We can also have cations go towards our cathode. So, okay. That is the galvanic cell itself. We can also take basically the same idea and add energy in there to produce our electrolytic cell. It's a little bit more complicated than that. We're going to look at what's called shorthand notation. For a galvanic cell. So here we have some sort, so we have the anode, then the salt bridge, then the cathode. So if we have something like this, so this would be what a shorthand notation looks like, where our anode and cathode portions are put in here. Salt bridge is shown with 2 lines. Single lines is a phase boundary. And you guys are going to have to produce these shorthand notations as well as take these shorthand notations and tell me what's actually going on. So in this case we have zinc solid, oxidizing to zinc 2+ to produce 2 electrons. And then our other half reaction, Cu2+ is taking 2 electrons to produce Cu solid. So they're pretty simple. If you have any electrodes in there that aren't part of the actual reaction, those will also be included in there, and we'll go over all of that in class. Okay. Along with in the actual full-length lecture videos. Next thing I want to look at is the cell potential of these. So we have a cell potential for these electrochemical cells, and it is basically in volts, which is equal to 1 joule per coulomb. Okay, and it's the force that pushes electrons from the anode towards the cathode. It's based on reduction potentials. So how much a substance wants to be reduced or how little a substance wants to be produced. We solve for our cell potential as E naught cell, so it's the standard, right, is equal to our oxidation half plus our reduction half, where our oxidation is the negative of its reduction. Okay, or we can look at it as the E cell is equal to the reduction potential of the cathode minus the reduction potential of the anode. These are both reduction potentials. And these, on the other hand, this is a reduction potential. This is an oxidation potential. So, just 2 ways of looking at it. So, if we have a reduction potential, it talks about how easy it is to reduce. So, if this value is greater than 0, it is easier to reduce than hydrogen, than H+. So these values, and one second, if our reduction potential is less than 0, it means it's harder to than H+. So we use H+, this following reaction, 2H+, plus 2 electrons, gives us H2. This is kind of the standard that's used, and it has a reduction potential of 0. So anything that is easier to reduce than hydrogen has a positive reduction potential. Anything that is harder to reduce than hydrogen has a negative reduction potential. And all metals have been compared to hydrogen in what's called a standard hydrogen electrode. So you have a standard hydrogen electrode called She, and it's used to determine the reduction potential of metals. Okay, so we're going to use all that information and a table of reduction potentials, which you guys have been given already in this table right here. So these are a bunch of reduction potentials. Well, we're going to use those reduction potentials to determine our E cell in this lecture. And that, we'll do math in this, but it's going to be kind of, that's about it for the math in this particular chapter, or in this particular part of the chapter. So using our potentials right here, our reduction potentials, we'll be able to determine our cell potential for different redox processes. And that's everything for our pre-lecture for lecture 20.